going to be working the homework solutions for 3-3 or 3.3, derivatives of logarithmic and exponential functions. So I guess there's some major formulas we need to know for this section. Just as a reminder, if you have e raised to some power u, that the derivative of this will be itself times the derivative of whatever was up here. Also, if we have natural log of u and you want to take the derivative, it'll be 1 over u times the derivative of whatever the u is. Another way you could write that is u prime over u. And then if you step away from the natural log and the natural exponential functions, you get more general. The formulas we have are a raised to the u, where a is a number here and u is some function of x. The derivative of this will be a to the u, so itself, times natural log of the base, that's natural log of that number, times the derivative of what was up here. And then if we have log base a of u, the derivative of this will be 1 over u, just like over there, but then we have to multiply that by natural log of the base on the bottom, and then times, because of the chain rule, u prime. So those are like the main formulas for this section. These are the very general ones. They work for any base, or well, any exponential function with, how do I say this? Okay. This works for any base as long as the a is positive and it's not 1. And same thing here, as long as that's positive and not 1, then this formula works. If the a is the e, right, which is a very special number, then we get these two formulas. All right. There are a lot of problems in this section, so I think I won't do every single one of them. First one, though, I'll do. F of x equals log base 10 of x cubed plus 1. And we're asked to differentiate the function. So I'm just going to find the derivative of this function with respect to x. F prime of x will be equal to, well, we have log base 10 of u. Here's u right here. So the derivative of log of something is 1 over the u, x cubed plus 1, times natural log of whatever the base is. And the base here is 10, so natural log 10. And then times the derivative of what was in here. The derivative of what's in there is just 3x squared. So you could rewrite this as 3x squared over x cubed plus 1 times natural log of 10. That's it. This is just a number. That's just a number. And then you have your x squared, and then in here we have to have this in parentheses because this number would distribute through if we were to actually want to, you know, like if we plugged in a number here for x, we could figure this out multiplied by this. But if we leave it as a variable expression, then you would have to distribute this through. If you don't have the parentheses, then that doesn't mean you're going to distribute. So put it there. All right, number 2. F of x is x ln x minus x. So when we look at this, I hope that you recognize that we have two terms, right? One term, two terms, so I can differentiate these separately. And then on this one, I have multiplication, which means I'm going to have to do a product rule right there. So when I take the derivative of this, let me do derivative of this, which is going to be the derivative of the first function times the second, plus the derivative of the second function times the first. So the derivative of the first function, the derivative of x with respect to x is 1. I don't need to write that, but I'm going to. Times natural log x plus the derivative of natural log of x. So natural log of x, that's a special one. Remember, derivative of natural log of u is equal to 1 over u times u prime. Well, if u is x, right? If u is x, then there's going to be 1 over x times the derivative of x, but the derivative of x is 1 because we're differentiating with respect to x. X is our independent variable. So this just turns into 1 over x, that's the derivative of this, times x, and then we have minus the derivative of x, which was just 1. Again, because the derivative of x with respect to x is 1. And then I can go about cleaning this up a little bit. We have, this is just natural log x. 1 over x times x, that's just 1, so plus 1, and then I have minus 1. Hey, that's just natural log x. All right. Number 3. F of x is sine of natural log of x. So I hope you recognize that this is composition. You have sine of, not times, sine of natural log x. So we have to do chain rule here. And we start with the outer function. So the outer function is sine. What is the derivative of sine of something? Well, it's cosine of that something. And then we go inside, after we've done derivative of sine, we go inside, take derivative of natural log of x. Well, we just did that. That's just 1 over x. And this is it. You can just leave it like this, or you can move the 1 over x out in front. Or you could even write like this, cosine natural log x all over x. So just like slide that x underneath. All right. These are going pretty quick. 4. F of x is natural log of sine squared x. I see, this could be a little tricky. Let me do it the way most of you would probably do this. You would say, all right, I see that I have composition. I have natural log of sine squared x. This right here is also composition. But let's just look at this, everything in here, let's look at that as being u. So the derivative of natural log of u is equal to 1 over u. So 1 over sine squared x times the derivative of what's inside. So we have to take the derivative of sine squared x. And remember that sine squared x is the same as sine x squared, right? So if I were to ask you to take derivative of this, you'd bring the 2 out first. So I'm going to have 2. Then you'd have this to the first power, which is just sine x. And so you would have done the 2, right? 2 came out, that turned into a 1, that's this. Then you would say, okay, forget that, take derivative of sine of x, that's cosine x. And if you kind of clean things up here, you'll notice that one factor of sine cancels out with one of the factors there. And you just get 2 cosine x on top, and then you just get a single sine x on the bottom. And that's 2 cotangent x. Remember, cosine x over sine x is cotangent x. Sine x over cosine is tangent, so if you flip it, it's cotangent. So that's what we get. Now, I want to do this a slightly different way. That's correct, we're done, everything's good. I want to try this a little different, though. I want to go back up to this one right here. And I want you to agree that this is the same as sine x is natural log of sine of x squared, because that's what this means, right? This means that. So if I do that, and then I go back to college algebra, and I remember this property of logs. If I had natural log of something to the n power, we can bring the n power out front. This was a major property in algebra, is that n can drop out in front and become multiplied. Very, very nice formula. And so what I realize here is I have natural log of, this is like the x, natural log of x squared. Natural log of x squared, that 2 can come out. So I'm just rewriting, I'm not taking a derivative. Do not think that I'm dropping the 2 out in front because I'm doing derivative. I'm just using properties of logs to rewrite the problem. Now I will take the derivative. When I take the derivative of this, 2 is attached to the front. It's a constant. It's going to come for the ride. Derivative of natural log of u. Okay, this is going to be my u here. Derivative of natural log of something is 1 over it, 1 over that something, times the derivative of what's in here, which is just cosine. And you'll notice here I get 2 cosine x over sine x, right? Just that cosine and the 2 come on top. And that's exactly what we just had. That's 2 cotangent x. I just want to point that out, that we could have done that. Number 5, natural log of 1 over x. Y equals, oh, f of x equals. Again, I see 2 different ways we could do this. Let me show you one way. One way would be, we could recognize this as natural log of 1 minus natural log of x. So what I did there is I used, again, a property from college algebra. You have natural log of x over y is equal to natural log of x minus natural log of y. We used this in college algebra when we were doing something called expanding and condensing log expressions. If you have division inside of one log, you can split it in 2 logs with subtraction between them. That's what I've done here. Then I can look at this and say natural log of 1, well, that's 0. And that's just something we have to know. Natural log of 1 is 0. So all I would have is negative natural log x. That's what that is. And there's an even crazier way you can see that it's this. If you rewrite this, you could rewrite 1 over x as x to the negative 1. Then you could use a property we just used a second ago and drop the negative 1 out front. And you would have this. So rewrite this as that, drop it out, you get this. I have not done any derivatives here. All I'm doing is showing you that that could be rewritten like this. 2 different ways. And now when I come to take the derivative, just take derivative of this. Negative 1 sitting in front is going to come for the ride. I'll even put negative 1 times, now what's the derivative of natural log of x? 1 over x. So the answer is negative 1 over x. And we'd be done. Now let's say that you didn't do that. Let's say you didn't simplify this and make it look like that. Let's say you just attacked that right there. Then you would have had composition, natural log of something, right? So you would have said, all right, well, the derivative of natural log of something is 1 over that something, which is 1 over x, times the derivative of what's in here. So when you look at that right there, if I want the derivative of that, I could rewrite that as x to the negative 1, take its derivative, power rule, negative 1 comes out, subtract 1 from this, x to the negative 2. So I would have this. This times negative, can I rewrite this as negative 1 over x squared? Sure I can, like that. That's what this is. I don't like that negative, I'm gonna put it up here. So it's this times this. And when you have 1 over a fraction, you can just flip the fraction over. So this is really just x over 1, which is x, times negative 1 over x squared. And then one of the factors of x cancel out. And you're just left with negative 1 over x, which is this. I think that's a little easier doing it this way personally. But you can see you get to the same answer. Isn't that nice about math? That you get to the same answer? As long as you do all your steps correctly, you don't break any rules, we should get to the same answer. It'd really, really suck if we got different answers depending on how we did it. Okay, y equals 1 over natural log of x. All right, this is different than the last problem. Last problem was natural log of 1 over x. So the fraction was inside the log. Here, the log is inside the fraction. All right, so we have to approach this a little different. I know you might be sitting there going, well, I could do a quotient rule, right? Which I agree you could. But what I'm going to do is I'm going to rewrite this as natural log x, the entire thing to the negative 1. Because that's what that means, right? If I have something to negative 1, I just drop it down as a fraction, it would become this. And then on this, I'm going to use chain rule. I have something to the negative 1. I'm going to take the derivative, right? So negative 1 is going to come out. I'm going to subtract 1 from that power. Then I'm going to go inside and take derivative of what's in here. So the derivative of this should be the negative 1 popping out. Then I have natural log of x raised to the negative 2 because I subtract 1 from the power. Chain rule says times. Now go inside. What's the derivative of natural log of x? It's just 1 over x. Now I'll just clean up. This drops down to the denominator. That's a negative 1 out front. So I have negative 1 over natural log of x, the entire thing squared. And then I still have 1 over x over here. And I'll do one more step, negative 1 over, I'm going to put the x in front of this, x, and then the entire quantity natural log of x squared. Now I want you to be mindful of this. This right here, natural log of x, that whole thing squared, is not the same as natural log of x squared. Here, the squaring is occurring on the x. Here, the squaring is occurring on the entire function. On this one, we could drop a 2 down using properties from college algebra. On this, you cannot drop the 2 down because the 2 is not on this piece, on the argument of the function. It's on the entire thing. So when I was here at this point, I'm just going to stop. I can't really do anything here. All right, number 7. All right, f of x is sine 5x, natural log 5x. Wait, sine x, natural log 5x. That's the way it's written. So we need to understand that there's a product right here. That's multiplication. It's multiplication of 2 factors. It's sine x times the natural log of 5x. So I'm going to have to apply product rule right here. The derivative of this will be the derivative of this times this plus the derivative of this times this. So the derivative of this first one is just cosine x times the second one plus, now the derivative of this one. This is chain rule. Derivative of natural log of u, right? Natural log of u is 1 over u times the derivative of what's in here, the derivative of u, which is just 5. But this is right here we're done with the derivative of this. But because this was coming from a product rule, we have to say times this first function. Right there. And notice these 5's cancel. Like that. And there's not a whole lot more I can do to clean this up. This is going to be cosine x times natural log 5x plus sine x, that's this right here, but I had an x on the bottom over x. And don't tell me that this goes to 1, because we're not taking a limit, right? We're not letting x go to 0 or anything. This is just the derivative of the function. So that's it. 8. I got to go all the way to 15. All right, f of x is log base 5 of x times e to the x. All right, now we're finally getting some exponential functions in here. All right, again, several different approaches to this. You could just go, let me just attack it just without doing any simplification first. If I do the derivative, I'm going to use chain rule, derivative of log of u, here's u, derivative, sorry, not log base 5 of u, the derivative of log base 5 of u is going to be 1 over u, so 1 over x e to the x, times natural log of 5. That's the formula I had on the board earlier. Derivative of log base a of u is equal to 1 over u times natural log of a. Times, now I need derivative of what's inside the log, and I have to realize that that's a product. So I'm going to have product rule. I'm going to give myself some room for it, put it in parentheses. Derivative of this times this plus derivative of this times this. So derivative of x is 1 times this plus derivative of e to the x. It's the first time we've done this. Formula I gave you earlier. derivative of e to the u is itself times the derivative of what's up here. So if this is e to the x, take derivative, it's itself times the derivative of x, which is just 1. So the derivative of e to the x is just itself, e to the x. And then times the first one, x. And then what I could probably do, I see something, I could rewrite this. This is going to be on the top, e to the x plus e to the x times x over x e to the x times natural log 5. Notice that I have an e to the x down here, I have an e to the x here, and e to the x here. I can factor an e to the x out of the top, and then on the bottom, I have that e to the x. Now I can cancel this factor. And so I get 1 plus x on top over x times natural log 5. There you go. Now let me approach the problem slightly different. I'm going to go and I'm going to use a property of logs before I start taking the derivative. So again, going back to college algebra, if you have log base a of x times y, this is the same as log base a of x plus log base a of y. So it says that you can split, if you have one log with multiplication, it splits into 2 logs with addition. So there's my multiplication inside a log. So I can rewrite this as log base 5 of the x plus log base 5 of the e to the x. Right? I'm going to leave this right here. We could go even further right now. I just don't know if it's going to look like the answer when I'm done with it. Let me just go straight from here, take derivative. What is the derivative of log of something? Well, log base 5 of something. It should be 1 over that something times the natural log of the base, so natural log of 5. I'm done with this, okay, because the derivative of the inside of this is just 1. Plus, now what's the derivative of log base 5 of e to the x? It's 1 over the e to the x, again natural log of 5. But then very important at this point, I have to now go inside and take derivative of what was in here. And derivative of e to the x we did earlier is itself. Then what happens is this e to the x and this e to the x cancel. And so you're left with 1 over x natural log 5 plus 1 over natural log 5. And that doesn't quite look like this unless we get a common denominator. If you get a common denominator, you can put these two together. So you'd have to introduce an x here so that these match up. Whatever I do at the bottom, I have to do at the top, so I introduce an x there. And then when I, oh, someone's coming in. Then when I, hold on. Hello, do you have a conference in here?
Yeah, we're going to have.
What time?
1:30.
1:30? Give me just a minute. I'm almost done. Okay. All right, so if we put these two together with a common denominator, then you get 1 plus x over this, and that's the same as this. So you can see you get the same result both ways. I'm try and do number 9 real quick. I'm about to get kicked out of here. Number 9, natural log. Wait, g of x is natural log of a minus x over a plus x. Now a in this problem is a constant. They don't put the parentheses around it like I did, but it's understood that there's parentheses there. So I'm actually going to use the property of logs to do this problem. So if I have a single log with division inside, I can break it up into 2 logs with subtraction. So this is college algebra. And now I'm ready for the derivative. The derivative of g is the derivative of natural log of u, or something, right, is just 1 over that something times the derivative of what's in here. Well, derivative of a is 0 because it's a constant. Derivative of x is 1, but I have subtraction. So I should just get negative 1 out of that when I take derivative. Then I have, let's see, minus, now I do derivative of this one, which is again 1 over what's in here, times derivative of what's inside, which is just 1. So I get, let's see, this is negative 1 over a minus x minus 1 over a plus x. And I'm wondering if they get a common denominator and put these together as the answer in the book. I don't know. I'm going to leave it like that because I'm under a time crunch here. I really need to do more of these. I don't know if I'm going to have enough time later today. So maybe tomorrow morning I'll do it. And that was only 25 minutes. Okay, looks like I can get this room back for just a little bit. Okay, I was on number 10. So number 10, you have a different variable, different independent variable, f of u. And we have u over 1 plus the natural log of u. So u is like the x. All right, so I see quotient rule here. Because I have two terms down here, I can't like split this into two different things. So I'm just going to apply the quotient rule. So the derivative of this should be the derivative of the top. The derivative of u with respect to u should be 1 times the bottom minus the derivative of the bottom. So we have two terms down here. So the derivative of 1 is 0. The derivative of natural log of u is the same as us saying, what is the derivative of natural log of x? Because again, u is like x is here because it's the independent variable. So derivative of natural log of u should just be 1 over u. All right, that's the derivative of the bottom. Then times the top. Then all over the bottom squared. So when I square the bottom, I get 1 plus natural log u, that whole quantity squared. Now this just becomes 1 plus natural log of u. Then this is going to become, right here, that's a 1, so minus 1. And then over 1 plus natural log of u squared. The 1's cancel, and you have natural log u over 1 plus the natural log of u, that quantity squared. There it is. All right, number 11. We have g of x equals natural log of x times the square root of x squared minus 1. All right, we got a lot going on here. Got chain rule. We've got log and inside log. We got some stuff. I do notice there's multiplication here. I could split this into two logs, and I think I'm going to do that. So I'm going to do some algebra first. Multiplication inside of a single log turns into two logs with addition between them. And then I can go a little bit further. I realize that this is the same as natural log of x squared minus 1 to the half power. And if I have natural log of something to a power, that power can come out. So I'm really just doing a lot of algebra here just to help me get a nice clean derivative without having to do too much extra work. I think that's pretty clean right there. We cannot pull the 2 out because this is two terms, so the squared would have to be on both of them for that to happen. I also can't split this into two logs because the property works when you have multiplication inside. We do not have a property to split up a log when we have subtraction or addition inside. So that's as far as I can go. Now the derivative of this is derivative of natural log of x with respect to x. That's just 1 over x. And then plus a half that's going to come along for the ride. And now a little chain rule. Derivative of natural log of u, or of something, is going to be 1, that's multiplication, 1 over this times the derivative of what's in here. Two terms, derivative of x squared is 2x, derivative of 1 is 0. So we're just going to get 2x here. This 2 and this 2 cancel. This x will go on top. So I can rewrite that as separated here. This is equal to 1 over x out front plus, I had an x on top, I have x squared minus 1 on the bottom. And that's probably good enough. I could get a common denominator, but I'm just going to leave it like that. All right, let's compare that to number 12. H of x equals natural log of x, and instead of times, here they have plus square root of x squared minus 1. So this is a good problem. It's illustrating the fact that I can't do the algebra that I did on the previous one. I cannot do that here because that's addition inside of a log. And so there is no property of logs that allows me to split this up. So I've just got to attack it as it is. The derivative of this should be, derivative of natural log of something should be 1 over that entire something times the derivative of what's in here. I have two terms here and here, so I'm going to have parentheses. Derivative of x is 1 plus the derivative of this. Now another chain rule. Derivative of the square root of something is 1 over 2 times the square root of that something. Okay, times the derivative of what's inside, which is 2x. And that finishes off my derivative inside here. And all I can see here is that 2 and that 2 cancel. I have 1 over x plus square root of x squared minus 1 times this thing becomes 1 and then plus x over square root of x squared minus 1. I don't think I want to multiply any of that together. Although, oh no, they're not the same. Never mind. So that's it. I'll just leave it like that. The book might simplify that, but this is number 12, so that's not in the back of the book. It's good enough. All right, 13. So 13, these are starting to get uglier and uglier. We have capital G of y. So y is our independent variable. We treat it like x. Natural log, and then we have a fraction here. We have in the top 2y plus 1 to the 5th. And then over square root of y squared plus 1. Okay, just keep in mind that whole thing is inside that natural log. So I'm going to do some algebra first. I'm going to use the fact that if I have division in a single log, I can split this into 2 logs with division. So it'll be the numerator, all that stuff, inside of one of the logs, minus another log, and then this. And watch the way I'm going to write that. Write that to the 1/2 instead of square root. I'm doing that so I can pop these powers out. The power can come out. Again, that's not me doing a derivative. That's just me using properties of logs. Okay, and now here I will go ahead and take derivative. So g prime of y is, all right, 5 is going to come for the ride. Derivative of natural log of something is 1 over that something times the derivative of what's inside. Derivative of what's inside is just 2. That's kind of like the 2x, right? So derivative of 2x is just 2. Derivative of 1 is 0. So that's it. That's all I have there. Minus 1/2 is going to come for the ride. Derivative of natural log of something is 1 over that something times derivative of what's inside here, which again, y is like the x, so this is just going to be 2y. And then derivative of 1 is 0. So that's it. I can cancel these 2's. Over here, I can put this 2 and that 5 together. So I should get a 10 on top, and then 2y plus 1. And then I'll have a minus, right? There's a minus. And then the only thing left over here is a y on top and a y squared plus 1. That looks good. Number 14. A little g of r is r squared times natural log of 2r plus 1. All right, so r is like the x here. R is the independent variable. And so we're going to treat it like that. And I have a product right here. I can see that product rule right there. I'm going to go ahead and just go right for the derivative here. So it's the derivative of the first one times this, derivative of this one times this. So derivative of r squared is 2r times the second one, plus derivative of natural log of something is 1 over that something, times derivative of what's inside of it, which is just 2, times the first function r squared. And I suppose we could just rewrite it, clean it a little bit. I can just put this 2r squared on top, so 2r squared over 2r plus 1. There we go. All right, number 15. Capital F of S, S is the independent variable, is natural log, this is the way they write it, natural log S. So what that really means is natural log of S. So you have S is sitting inside of a natural log, but that natural log is sitting inside of another natural log. So this is chain rule. The derivative of this, we start with the outside. The derivative of natural log of something is 1 over that something. 1 over that something is natural log S times, now I've done this, the derivative of what's in here, derivative of natural log of S is 1 over S. And then times the derivative of what's inside here, derivative of S is 1 because it's our independent variable, so 1. So this just becomes 1 over, if I multiply this times this, I could write it like this, S natural log S. That's it. Man, my S's look like 5s. Where am I? 17. Y equals tan, and then they're going to use a bracket, but remember brackets just like a parenthesis. Tan of natural log, parenthesis, ax plus b, close parenthesis, close bracket. So we have composition again. Tangent of natural log of a linear expression. So I'm going to start from the outside and work my way in. Y prime, and the independent variable here is x. We're assuming a and b are constants. So derivative of tangent of something is secant squared of that something. I don't have to use brackets. I'll use them reluctantly. Okay, that's derivative of tangent, so I've done that. Move inside, derivative now of natural log of this. Derivative of natural log of something is 1 over that something. Okay, so I've done derivative of natural log of something. Times the derivative of what's inside. A constant times x. Right, constant's going to come along for the ride. Derivative of x is 1, so that's just going to be a. And then derivative of that constant is 0. So I would have a parenthesis here if I had more than one term, but I don't. It's just a. So what I could do for a final answer is just slide this a on top. I can move that whole fraction out in front of the secant squared, or just leave it at the back. All right. 18. Ooh, that doesn't look good. Capital H of z. Z is the independent variable. Is natural log of the square root of a squared minus z squared. Z is our variable, a is a constant, over a squared plus z squared. All right, I'm going to do some algebra first. This is natural log of a squared minus z squared over a squared plus z squared. All of that to the 1/2. That's what that means. Check something here. Okay. Now, the reason I did that is because I want to pop that 1/2 out. Because I have natural log of something to a power, that power can drop out. So this will be equal to 1/2 sitting in front of natural log of a squared minus z squared over a squared plus z squared. And now I have division inside of a log, which means it splits into 2 logs. But keep in mind I have a 1/2 sitting out in front of all that. So when this becomes 2 logs, it'll be this first log minus, because it's division, second log has the denominator in it. Now, the 1/2 can distribute through. So there'll be 1/2 in front of that and 1/2 in front of that. I don't want to write all that again. I'll just leave it. Let's go ahead and get a derivative. H prime of z should be, let's just let 1/2 come for the ride because it's attached to all that. So 1/2, and in parentheses, I need to take derivative of this. Derivative of natural log of something is 1 over that something times the derivative of what's inside. Now we're differentiating with respect to z, so derivative of a squared is 0, it's a constant, so that's gone. Now derivative of negative z squared, the 2 comes out, we get negative 2z. And we're done here. Now we move on, minus derivative of natural log of something is 1 over that something. I need to erase this. 1 over that something times derivative of what's inside, 0, and then derivative of that's 2z. And then all that's in parentheses because of that 1/2 out there. And if I distribute a 1/2 through, watch, when I distribute 1/2 through to this thing and then to this thing, it's going to kill off this 2 and that 2. So I should have just the negative z that was here over this. So negative z over a squared minus z squared. And then I'm going to have a minus, and then here I'll have a z. So minus z over a squared plus z squared. I'm happy with that. Number 20, root x times e to the x. Product rule. You see that product between those two? Okay, so the derivative of this is the derivative of the first one times the second one plus derivative of the second one times the first one. So just remember, derivative of e to the x, right, on that second one is itself, and then times the first one. Derivative of root x is 1 over 2 root x, then times the second one. So there's your product rule. Yes, you could clean it up. You could even factor out an e to the x. Not necessary, but let me just show you. If I did factor out an x, this is what I would have. And then I could even get a common denominator. I could multiply the bottom here by 2 root x, top here by 2 root x. If I did that, I would have e to the x. And then this right here would become 2 times x, because root x times root x is x. That's 2x plus 1, so 1 plus 2x. Then over my common denominator, 2 root x. I mean, this would have been correct, okay, with that gone and that gone, but I'm just showing you, you could get that also. That one wasn't too bad. Am I almost done? Oh my gosh. Okay, 22, e to the x over 1 minus e to the x. All right, quotient rule here. Quotient rule. Derivative of the top is itself, times the bottom minus derivative of the bottom. Derivative of 1 is 0. Cover up the minus. Derivative of e to the x is itself, but it's minus. So negative e to the x times the top, which is e to the x, all over the bottom, which is 1 minus e to the x squared. All right, let's try and figure out what this is. This is e to the x minus e to the x minus e to the x squared, right? That's what that would mean to multiply it times itself. But if you multiply these two, you get e to the 2x. So that's what that second multiplication gives you, minus e to the 2x. And then minus minus is plus. Then again, e to the x times e to the x is e to the x squared, which is e to the 2x. Ah, look at those, they're going to cancel. All over 1 minus e to the x squared. This goes away, this goes away. All you're left with is e to the x over this. Interesting. I know I'm going fast, but this is a lot of problems. 24. Y equals e to the negative 2t. T is the independent variable here. Cosine 4t. Product rule. You have a product right there. So y prime will be the derivative of the first one. Now we have to be a little careful here. Derivative of e to anything is itself. So I put e to the negative 2t. But then I have to do chain rule. Times derivative of what's up here with respect to t, that'll just be negative 2. Okay, so I'm doing product rule, so that was the derivative of the first one is done, times the second one. Plus, now derivative of the second one, this is chain rule. Derivative cosine of something is negative sine of that something times the derivative of what was inside, derivative of 4t is 4, and then finish off the product rule, e to the negative 2t. Clean up time. Negative 2 times this, I'm just going to put negative 2 e to the negative 2t cosine 4t. And let's see, we're going to have a minus here also. So minus 4. I have an e to the negative 2t again. Then this time sine of 4t. And I also see a GCF, even though, I mean, I could say I'm done. I'm just going to show you. You could pull a negative 2 e to the negative 2t out. Right? They both have negative 2. They both have an e to the negative 2t. So if I pull the negative 2 out, all that's left here is the cosine 4t. And then I pulled the negative 2 out, so I'll have plus 2 and then sine 4t. That's 24. Y equals 5 to the negative 1 over x. All right, so this is kind of like e to the something, except instead of e, we have a to the something. And we talked about that, or I showed you the formula for that at the beginning. So the derivative of this, the derivative of a to something is itself times natural log of a, so for us natural log of 5, times the derivative of what was up here. Now remember, that's the same as negative 1 x to the negative 1. So if I pop that x up, this is what I have. If I take derivative of this, negative 1 pops out, you get positive 1, x to the negative 2. That's the same as 1 over x squared. So the derivative of this top piece is just 1 over x squared. That's it. All right, 28. Y equals e to the u minus e to the negative u over e to the u plus e to the negative u. All right, let's try quotient rule. Derivative of the top, two different terms, we'll do them each one at a time. Derivative of e to the u, oh yeah, u is the independent variable, so it's like the x. E to the u derivative is itself. Okay, I'm still doing derivative of the top, minus derivative of e to the negative u is itself, but be real careful here, times the derivative of what was up here, which is actually -1. All right, we didn't have that happen here because the derivative of what's up here is 1, so we had a 1 out here, but we didn't need to write it. That's the derivative of the top, times the bottom, with no derivative, minus the derivative of the bottom, okay. Derivative of e to the u is itself, plus the derivative of e to the negative u, we just did that, it's right here. It's going to be e to the negative u times -1. Okay, so that's the derivative of the bottom, then times the top, all of this over the bottom squared. Okay, that looks ugly. I'm not done. Clean up time. Equals. All right, this is, let me just try and save myself some time. This minus minus become a plus, so that is not there. Okay, and then over here, let's see. This minus and this plus turn that into a minus, and then this isn't here. And notice that this and this together, they're the same thing. So this is e to the u plus e to the negative u squared minus e to the u minus e to the negative u squared again, all over e to the u plus e to the negative u squared. Yes. Okay, I'm happy with that. Now, I should have paid a little more attention to this, but notice that if I split this back up into two fractions, this over this and this over this over this is 1. Then we'll have minus, because that's a minus, this over this, which I could write as e to the u minus e to the negative u over e to the u plus e to the negative u, all of that squared. So instead of squaring each one top and bottom, I just put them in a parenthesis and squared it. I'll leave it like that. 33. Man, this is a lot. I think this is gonna be my last one because I've got to go. 33. All right, 33. Y equals natural log of e to the negative x plus x e to the negative x. All right, now you could just go with the straight derivative here and go after it. I'm going to do some algebra first, watch. I'm going to factor out an e to the negative x and be left with 1 plus x. You see that? This has an e to the negative x, that has an e to the negative x. I just pull it out here and this is what I would have. So if I distribute this back through, I get that. Now I've created a product which allows me to split this into two logs with addition between them. So it'll become the log of the first one plus the log of the second factor. And that's really nice because when you put natural log and e together, they're inverse functions, they kill each other off. All you're left with is what's up here. That's just negative x. Then plus natural log of 1 plus x. Wow, that is really clean. I can take derivative of that very, very easily. Derivative of this, derivative of negative x is negative 1. Plus, the derivative of the natural log of something is 1 over that something. Times the derivative of what's in here, which is just 1, so I don't really need anything there. Well, that is a super clean derivative. Yeah, I guess that's a good place to stop for today. So I got through, I'm going to pick up on 41 when I come back. So I have 1, 2, 3, 4, 5, 6, 7 problems to do tomorrow. Where were we? Okay. We are on number 41. Y equals e to the alpha x times sine of beta x. And this is number 41. You're asked to find y double prime. All right, well, first let me just explain that alpha and beta are constants, like A or B or C or D. Normally we just imagine that those are just numbers, they're fixed. We don't know what they are. So try and take this derivative, recognizing that we have a product right here. Okay, it's e to the alpha x times sine beta x. So I'm going to apply the product rule. So the derivative, first derivative, will be the derivative of this times this, plus derivative of this times this. So derivative of e to the alpha x, well, derivative of e to anything is itself, times the derivative of what's up here. So remember, alpha x, taking that derivative, is the same as me saying something like, what's derivative of 4x? You just say 4 here is just alpha. So it's just a constant. So it's going to be alpha here. And then times the second function, sine beta x, plus, so I'm doing product rule here, derivative of sine of beta x. Well, derivative of sine of something is cosine of that something. And then chain rule says go inside and take derivative of beta x, which is kind of like this here. So all we get is beta. And then finishing off the product rule times e to the alpha x. So we have alpha, I'm going to put the constant out front, alpha e to the alpha x sine beta x plus beta e to the alpha x times cosine beta x. All right, so there's my first derivative. Now I can go and take the second derivative right now. And just do each one separately because there's two terms here. Or I could notice that they both have an e to the alpha x and factor it out. Kind of my choice here. I think I'm going to factor out the e to the alpha x. Let me do that. E to the alpha x comes out. That leaves me with an alpha and a sine beta x plus a beta and a cosine beta x. All right, so there's my first derivative. Now let's take the derivative of that. It's going to be ugly. All right, so we have again a product rule right here. Here's my product. Derivative of this times all of this plus the derivative of all of this times this. So y double prime will be the derivative of e to the alpha x, which we did already. E to the alpha x times alpha. So that's derivative of this times all this. Alpha sine beta x plus beta cosine beta x. Okay, plus, now I take derivative of all of this. Two separate terms. So I'm going to do derivative of this one first. Keep in mind alpha is a constant, so it's going to come along for the ride. So constant coming along for the ride. Derivative of sine of beta x is cosine of beta x times beta. Remember, because chain rule, right? Take derivative of sine of something, you get cosine of it. Take derivative of what's inside. Derivative of beta x is just beta. So that's a derivative of the first piece, plus beta is a constant, comes for the ride. And then derivative of cosine of something is negative sine. So I could put negative sine here, but I'm going to just change this to a minus. And then I'm going to have beta x. All right, that's derivative of cosine of something is negative sine of it. And then derivative of inside, derivative of beta x is beta. So I'm done with the derivative of this thing. And then finishing off the product rule times the original first function, which is e to the alpha x. All right, clean it up, clean it up. Y double prime is, let's see here. How shall we do this? Let me distribute this alpha through to both of those. I'm going to leave the e to the alpha x out here. So I have alpha squared, because alpha times alpha is alpha squared, sine beta x, plus, now the alpha times the beta is alpha beta cosine of beta x. And that finishes off that. Then over here, let me just kind of put these together. I have an e to the alpha x out front, so I'll put that right here. And then inside here I have alpha times beta, so alpha beta cosine beta x. And then on this one I have minus beta times beta is beta squared, sine of beta x. All right. I'm looking to see if there's anything I can do here. I can collect like terms. All right, this next step is going to look a little weird. I have like two big chunks of stuff. I've got this thing and I've got this thing. They both have e to the alpha x, so I'm going to factor out an e to the alpha x. And then I will have this plus this plus this minus this. So when I take this away and take that out, I'm just left with what was in the parentheses here in both of them. I can put it all together. So I'll have alpha squared sine beta x plus alpha beta cosine beta x. And then over here I have another alpha beta cosine beta x. And then over here I have a minus beta squared sine beta x. And I have some like terms here. These are the same. So that becomes 2 alpha beta cosine beta x. And notice, oh, I forgot my parenthesis here. Notice that this is sine beta x, this is sine beta x. So I could factor a sine beta x out of each of just those two. So I could write this plus, let me do it this way. If I just have those two pieces right there, I'll do it up here as scratch work so you can see what I'm doing. I have alpha squared sine beta x minus beta squared sine beta x. So I pull out a sine beta x. That would leave me with alpha squared minus beta squared. And I could rewrite this the other way, which is the way I'm going to do it. I'm going to write this as alpha squared minus beta squared times sine of beta x. Okay, but all of this has an e to the alpha x in front. There you go. Now, I'm curious if that looks like the back of the book. I'm going to check to see if that looks like theirs. This was number 41. Wow. That's almost exactly the way they have it written. That doesn't happen very often. The only thing they have different is they have this here and this one here. But other than that, they're the same. That's a good problem. I like that one. All right, next one, 43, x ln x. Okay. All right, so let's do the first derivative here. They're asking for the second derivative again. So we have to take derivative twice. So the first derivative, we have a product rule right there. So derivative of the first one times the second plus the derivative of natural log of x is 1 over x times the first one. This is just natural log x. That's natural log x plus, this is just 1. And then y double prime is going to be the derivative of this. Derivative of natural log of x, just 1 over x. And derivative of 1 is 0. So that's it. Boy, that was almost too easy. Let's see. This was, yeah, okay. All right, 45. Y equals natural log of x squared minus 3x plus 1. And they give you a point here, 3, 0. And you're asked to find the equation of the tangent line to this curve at the given point. All right, so what we need, of course, to find the equation tangent line is we're going to use this. We already know y1 and x1. We just need to find the slope. The slope comes from getting the derivative at that point 3, 0. So I need the derivative of this. So y prime, we have that the derivative of the natural log of something is 1 over that something times the derivative of what's in here. Derivative of what's in there is 2 terms, so 2x minus 3, so I put it in parentheses, which I could rewrite as 2x minus 3 over x squared minus 3x plus 1. So that's our derivative. We want the derivative at the point 3, 0, so I'm going to replace x with 3 and y with 0. So at 3, 0, we get that y prime equals 2 times 3 minus 3 over, oh yeah, also there's no y in here, so that 0 really doesn't matter. That 0 is only going to come into play right here. Replace that with 3, so 3 squared minus 3 times 3 plus 1. So top is 6 minus 3 is 3 over 9 minus 9 is 0 plus 1, so that's 1, so our slope is 3. So coming back over here to the equation of the tangent line, we know that we get y minus 0 equals the slope 3 times x minus 3. And that means y equals 3x minus 9. So if I graph this line, it should be tangent to this curve at this point. All right, let's look at number 52. Now we're going to shift into a different type of differentiation, very important type of differentiation. Logarithmic differentiation. So number 52, we have y equals e to the negative x cosine squared x over x squared plus x plus 1. Now, if we just tried to attack this right away, like this, with quotient rule, it would be a mess, all right? So this is where the power of logarithmic differentiation comes in. And what I'm going to be trying to do is use all these properties of logs. Remember, log of x times y is log of x plus log of y, and then natural log of x over y is equal to natural log x minus natural log y, and natural log of x to the n power is n natural log x. So these properties that we had in college algebra, I'm going to try and use those. So what I realized is that I have division, right? I can split division up into two logs, right? If I have division inside of a log, but right now I don't even have a log. So logarithmic differentiation, what we're going to do is we're going to take the natural log on both sides of the equation, which we are allowed to do because the natural log function is 1 to 1. All right, now, once we have this, I can rewrite, be careful here, natural log y equals, now over here I'm just use properties. I have division, so I split this into two logs. It's natural log of the top minus the natural log of the bottom. Then I realize that I have multiplication inside of a log. This log will split into two logs. So I have, again, the equation, natural log of y. We want to write it as an equation the whole time. Natural log of e to the negative x plus natural log of cosine squared x. So I've split this log into two logs, but I still had the minus natural log of x squared plus x plus 1. And keep in mind, you cannot split this into three logs because this is addition. Then, the next step, I'm going to just use some properties here. Natural log and e wipe each other out, right? They're inverses. So they're gone, and you're left with just negative x. And then here, we have natural log of something to the second power. The 2 can drop out, right? Because remember, cosine squared x is really cosine x squared. And then if I do natural log here, the 2 can pop out in front. All right, so there. And then this minus natural log of x squared, can't do anything here, plus x plus 1. And I think at this point, I'm ready to take a derivative. Now, when we take the derivative using implicit differentiation, using this thing called logarithmic differentiation, we have to use implicit differentiation when we take the derivative. So I have to take derivative of left and right hand side. I'm taking derivative with respect to x. So what is a derivative of natural log of something? Well, it's 1 over that something times the derivative of what's in here. What's derivative of y with respect to x? What's the derivative of y with respect to x? Well, dy dx, but that's y prime. So this is going to be y prime equals, and now I can take derivative of all this stuff. Derivative of negative x with respect to x is negative 1. Plus 2 is attached with multiplication, so plus 2 times the derivative of natural log of something is 1 over that something times the derivative of what was inside, derivative of cosine x is negative sine x. And that's it, I'm done with that. And then minus the derivative of natural log of something is 1 over that something times the derivative of what's inside, which is 2x plus 1. So I have 1 over y times y prime equals negative 1 minus 2, now check this out. The minus comes from the minus right here comes out. I have sine x over cosine x. That's tangent. So I'm just going to put minus 2 tan x. And then here, I'm just going to slide this on top. So minus 2x plus 1 over x squared plus x plus 1. So I'm getting real close. I need y prime by itself right now. Right now, the left side says 1 over y prime. So I'm going to multiply both sides by y. This whole side by y. And then I'll get y prime equals negative 1 minus 2 tan x minus 2x plus 1 over x squared plus x plus 1, all times y. But what is y? Well, that's y. So I'm going to write that big ugly thing right here. E to the negative x cosine squared x all over x squared plus x plus 1. So I'd have to take that and distribute it through. Boom, boom, boom. But I'm just going to leave it like that. And let me see what the back of the book has. Oh, they don't have the answer for 52, do they? Yeah, I'm sure it's right. Okay, 54. No, 53 is next. Y is the square root of x minus 1 over x squared plus 4. Oh, x to the 4th plus 1. Oops. All right. Same thing. I could do chain rule with some quotient rule in there. Let me try this logarithmic differentiation. Take natural log on both sides. And keep in mind that this right here can be rewritten as that to the 1/2. Because the square root of that whole expression means raise the whole expression to the half. Now I'm doing that because I can drop the 1/2 out in front. Now I have the natural log of division, right? X over y. I can split that into 2 logs with subtraction. But remember there's a 1/2 in front. So natural log y equals 1/2 times natural log of the numerator, x minus 1, minus natural log of the denominator, x to the 4th plus 1. All right, and I'm actually going to distribute the 1/2 through. I don't like to have that many parentheses. There we go. So there's my expression. And now I will take the derivative. So implicit differentiation, the derivative on the left side is 1 over y prime. That's going to be the same every time. It's always going to be that. This side, 1/2 is attached. It comes for the ride. Derivative natural log of something is 1 over that something times derivative of what's in there, which is 1. Minus a 1/2, which is attached to the function, so it comes for the ride. Derivative natural log of something is 1 over that something, times derivative of what's inside, which is 4x cubed. That 4x cubed can go on top. So I have 1 over y times y prime equals, check this out, 1 over 2x minus 2. So I actually just multiplied the 2 through the bottom here. I have 1, 1, 1 on top, so that's it. Here, notice this 2 and 4, that becomes a 2. I'll have a minus 2x cubed on top. On the bottom, x to the 4th plus 1. Now I will multiply both sides by y. So I multiply this side by y, and we're going to do that every time. Multiply this side by y. That means multiply this entire side by y. The y's cancel here. The y on this side is actually that up there. So square root of x minus 1 over x to the 4th plus 1. So that's y times all this. All right. Oh yeah. Y is equal to cosine x to the x. Notice that there's a parentheses around the cosine x. So it's the whole thing raised to the x. Now this, I'm sure I mentioned in class, is one of the very unique types of functions that we can get because both your base and your exponent, both of them, right? Both of them. The base and the exponent both have a variable x in them. So it's not an exponential function because this is not a number, and it's not a power function because that's not a number. In other words, like x squared versus 2 to the x, that's a polynomial. This is an exponential, right? Because the 2's are in different places. But if you have x to the x, this is neither one of those because the x's appear in both places. So anytime this is a function of x and that's a function of x, you're going to have to use logarithmic differentiation. So I'm going to do natural log of y on both sides. Then I use the property that I can drop this power out. Don't need the parentheses anymore here. I'll put it. And now at this point we take the derivative. On the left side we get 1 over y prime. On this side we have a product rule. So the derivative of the first one times the second one plus the derivative of the second one times the first one. So derivative of the first one is 1 times the second one plus the derivative of natural log of cosine x is 1 over cosine x times negative sine x, which is the derivative of what's in here, times the first function, x. So that's product rule. This is 1 over y times y prime equals natural log cosine x minus x sine x over cosine x, right? This is minus, so that becomes minus x sine x over cosine. Sine over cosine is tangent. Let me write it that way. Minus x tan x. And then I'm going to multiply both sides by y. So I'll multiply this side by y, it's going to go away, right? Multiply this side by y. Well, what is y? Cosine x to the x. That's what y is. So these are gone. Y prime equals this. We're done. And 62. Find the equation of the line tangent to the curve x e to the y plus y e to the x equals 1 at the point 0, 1. All right, this is an implicit equation in the fact that we cannot solve for y or x easily. So we want to, come up with this formula here, but we need to find m. M is going to be dy dx, or if you'd like, y prime, right? It's that at the point 0, 1. That's what m is. So I need to find y prime. So I have to take derivative of this implicitly on both sides. So what is the derivative of the left side? Well, that's a product rule, and that's a product rule. So let's do a quick product rule here. Derivative of this times this plus derivative of this times this. The derivative of x with respect to x is 1 times the second function plus what's derivative of e to anything? Itself times chain rule, derivative of what's up here, derivative of y is y prime, or dy dx. But then I have to finish off the product rule, so times x. So there's your derivative of the first one times the second one, plus here's the derivative of the second one times the first one. Then we go to the next piece, plus another product rule. Derivative of the first one, derivative of y is y prime, times the second one, plus the derivative of e to the x. Derivative of e to the x is itself. And then you could say times, from the chain rule, times derivative of what's up here, but derivative of x with respect to x is 1. So there's a 1 there, we don't need to write it. But finish off the product rule, you need a y there. And that must equal 0, which is the derivative of the right side. So you can see you have y prime in there, which is good, we need that, and we need it at this point. So at this point in time, I'm going to just replace x with 0 and y with 1. So let x be 0 and y be 1. We get e to the 1 plus e to the 1 times y prime times x, but x is 0, plus y prime times e to the 0 plus e to the 0 times y is 1. That must be 0. So notice on this right here, this term, this whole thing goes away because that's 0 times all that. And e to the 0 is 1. So that's a 1, that's a 1. We have e to the first power over there. So e to the first power is just e. This is just, e to 0 is 1. This is 1 times y prime. That's just going to be y prime. And then e to the 0 is 1. 1 times 1 is 1. So plus 1 equals 0. And if we solve for y prime here, we just take this and this to the other side. They both become negative. That's the slope of your tangent line. It's weird looking, but it's just a number, right? E is a number. So negative e is a number. Take away 1, still a number. Just going to plug that in right there. So the slope of the tangent line, the equation of the tangent line is going to be y minus y1 is 1 equals m, here's your slope, negative e minus 1 times x minus x1, which is 0. So you get y minus 1 equals negative e minus 1, that's this. Distribute that through to x, so times x. Or you could just say that's x, right? That's x times this. It's important that, since this is two terms, you have to put this in parentheses. And then add 1 to both sides. That's a weird looking equation of a tangent line, but it is the equation of the tangent line nonetheless. All right, that's it. 3, 3 is done.